Okay, guys, so in the previous class, I developed a preliminary version of the MATLAB code. So we're going to work on that to see the sense of control. That's what we're going to do eventually, because at the end of the semester, I'm going to back to this fully developed MATLAB code to implement the controller. So, but what we have done, we had a moving pendulum as a simple model of your leg. That's right. A particle pendulum of ML, and this was your hip joint that was moving with the x of t, and here was L. This angle was theta. Here was L sine theta, and here was L cosine theta. And we got, if you remember, the nonlinear theta double dot plus G over L sine theta was minus x double dot acceleration of the hip joint cosine theta. So we modeled your leg, moving leg, as a second order system because the order of the derivative here is second, that's right, theta double dot. And then we linearized around the equilibrium point of theta double dot, and we named this as the natural frequency square, I mean this term, of theta, and minus x double dot, and cosine theta was 1, if I remember, using the Taylor series expansion. Then I plotted the block diagram, that's right, for the first time. Block diagram in control, which is very important. Block diagram, and the block diagram was like this: plus minus, here was the error signal. This is the controller that's C controller, that's why you are taking the course. This sends you a control command, or U we say here, and then this goes to the plant. Oh, and we have a disturbance, sorry guys, we have a disturbance here. Let me show it with this D disturbance. Here we go, x double dot from the base. So this is being summed with the U control command, and here is minus, here is plus, this minus is for this. This goes to the plant, or the pendulum, moving pendulum, which is in the time series form, in differential equation form, is theta double dot plus omega n squared theta equals U minus x double dot. So when I teach you the controller, we're gonna add the controller here, as I told you. Guys, can you hear me? Yes?
Yes. Yeah.
So this gives you the real output, real angle that is being happened in unit time, theta real. This is being compared by sensor. We're gonna have a sensor, okay? So H, we named sensor, and give the output to be compared with the desired theta D, desired angle. For example, 45 degree pi over 4. And this gives you the error signal. And I told you in the control, one of the functions that you have, main functions, that you make error to 0. Okay? Okay, guys? Now, let me model this first because as I told you, I'm going to back to this model at the end of the semester in the MATLAB code. So, if this is the pendulum, I wanna make an animation of that in MATLAB. For those of you that you had no vibration with me, I'm just doing here. So ML. So here was again L sine theta, L cosine theta. So in MATLAB, this is how you plot this line. Okay, this line. You say plot. MATLAB, plot, bracket, x of this point. say coordinate of this point, because your coordinate system is here 0 and 0 is x and y. So x of and y of this point, center of the particle, is L sine theta, that's right, and minus L cosine theta. Am I right, guys? I'm just testing you. Am I right? Because the coordinate system was here, remember? No, I'm talking about the coordinate system from dynamics. I'm not talking about the... So guys, I told you, you are engineer. You have to follow every detail. The hip joint is moving with the x. See what I'm saying? Yes? So this is not 0. This is x. X of t. Remember in the code, x was, in the previous class, was sine of time. Remember that I told you as example? Yes? So here is not L sine theta. It's L sine theta plus x. See what I'm saying? Yes? The other coordinates of these 2 points, point A and point B. See what I'm saying? Anybody agree? Yes or no? If you have question, please stop me. Don't be shy. This is your class. You are here to learn. Okay? Not to be shy. Okay? So why this is minus? It's y component because this is under the datum. See here? Under the datum. So minus. So in the MATLAB, we say plot bracket x. I'm going to copy MATLAB. X of this point and x of this point. X of this point is L sine theta plus x bracket, comma. Now y of that is 0. Y of that is minus L cosine theta bracket, this process. By this command, I'm gonna make a movie of your moving pendulum. See what I'm saying? Yes? Now, how I model this? This circle? You know that the circle equation from high school is x of circle, center of the circle, x, plus r cosine gamma. Why? Look at, guys, this is a circle. If you take a point on a circle, and this angle is gamma, so it's x here, x of this point. Gonna be cosine gamma in r, and this is the radius of the circle. See what I'm saying? And this is xc. Look at here, xc, center, x component of the circle. So this is point on the circle P. So x of P is x of c plus r cosine gamma. Yes, this is simple trigonometry. And the y of that point is y of c, y of the center, plus r sine gamma, this component. What is gamma? Gamma is from angle 0. This is how we increment this step to 0.01 to 2 pi, because this point moving around is like this until 2 pi. This is how we create circle in the MATLAB. One of the ways. Another, there are lots of the simple ways in MATLAB. I'm just brainstorming that remind you trivial mathematics. Okay? Now, exactly I am doing this in MATLAB. Look at this, guys. I'm gonna open MATLAB. Let me hold this to save time. So everybody was clear about here, about this, what I developed? Yes? Hello? Can you hear me, guys? Can you explain? Yeah, because if this point was fixed, no motion, so the x of the circle gonna be only L sine theta, right? Yes, but this is moving by itself to the scale of x of t. So it's gonna be L sine theta plus x. If you remember that how we derive the equation of the motion, go and look at the r of p with respect to the point C. I mean this point, this say B, to the point A. See how I developed that? How I did it? Read it for me. Position vector R. Go to your previous class. What was R? Do you have the... See? This is just simple geometry. See what I'm saying? Okay, or kinematics in ME220 dynamics. Okay. No problem. So now let me open the code that we had developed in the previous class. Okay, you saw that I said natural frequency was 5 after linearization, and the disturbance was, I'm making to now for sine only, because, yeah, and this was minus, you know how I did it in the previous classes, right? This is disturbance, okay, and this is the omega n and theta after linearization, and we said I'm gonna make it 0, the angular velocity. So this is how we derived it, that's right. So here we go, for remembering to, here we go. See? And we started, for refreshing your mind, you started from initial condition of 45 degree, and because the base is oscillating, so you have a uneven, okay, amplitude of the vibration, because you have disturbance to the system. And this is the angle, remember? So for giving you reference, you can add x label, you know that in MATLAB, hopefully, it's time in second, and I say second, and I say font size, I say 14, okay, and the y label you can say is angle theta in degree, okay, font size 14. Now if I rerun it, you see that this is theta degree times second. Now you have it. What is this? Okay guys, done. So, and also we grid that. Now I want to see what's happening in reality. So guys, you saw that I told you when I write like this, the angle, this shows, as I taught you in the previous class, that all rows, this is the first column. See what I'm saying? So this gives you the angle of that. If I change it to, let me do that. If I, let me do that. If I say figure 2, I want to plot the angular velocity as the second state variable. I'm going to change it to, this is going to be, say, dot theta, and it's going to be radian per second. Okay, here we go. Figure 2. So this is the angular velocity of the pendulum. Yeah, angular velocity always in the radian per second. Okay, so okay, I plotted in the, I multiplied by 180 divided by pi to make it degree to be visible for you. See what I'm saying? But I cannot do that here. The angular velocity is radian per second always. See what I'm saying? In the S. Oh, okay. So when you write, okay, let me do this. Look at here, guys. Suppose x is equal to, just out of this example, okay, 1, 3, 4, 6, minus 5, minus 10. This is a vector, okay, in MATLAB. If I say give me x first row and the fourth column, what is the first row and fourth column? You tell me, sir, that you ask questions. This is first row. What is the fourth column? Yeah, must give me 6. Now, if I say give me this, okay, means give me the first row and all the columns. Here we go. Gives the x itself. See what I'm saying? This is the command word. Now, if your x is, let me tell you, x is 2, 3, the first row, minus 2, 1, the second row, 0, 0, third row, 5, 6, 4th row. Okay, this is it is 4 by 2 matrix, right? Now, if I say give me all the rows and the second column, it's gonna give me this. See what I'm saying? This is second column. Here we go. Okay, this is powerfulness of MATLAB. And that's why I told you, if you don't know how to work MATLAB, even that you're cum laude as engineer, you're nothing, absolute zero. Or Python, okay? Either of them. In this course, I'm going to focus on the MATLAB and Python, MATLAB and Simulink, okay? Okay. So by this assumption that you pass MATLAB in ME202, that's why I'm focusing on this, okay? So now you saw that, and let me change this to make it different. So, okay, so this is the angle of the pendulum based on the disturbance. It has uneven amplitude, and this is the angular velocity of the pendulum in radian per second. So now I want to make a movie of that, because I told you at the end of the semester we're not design controller. I'm going to back to this example. Okay. First, there's a command in MATLAB with the name of size. Let me do that. If his x is this, if I say size of x, it gives me 4 and 2, means it has 4 rows, 2 columns. Okay, size means this, 4 rows. So I'm gonna do this. I'm gonna size of moving pen, size of theta 1. Okay, I want to see based on this time scale that I develop how many rows this and columns this has. This angle of the pendulum. Look at here. Has how many rows? 2001. How many columns? 1. Because obviously it's 1. Okay. So I'm going to take this. You're going to tell me why. Because I'm going to develop a for loop in MATLAB. And I'm putting a counter from the first row increased by 1 to size of mole of pendulum. By doing this in the for loop, I'm reading all the rows of the angle, each 1 by 1. See what I'm saying? Yes? Bear with me. Figure 3. I'm going to show it how. Plot. Okay, guys, look at here. And I'm going to implement whatever I taught you here. I'm going to implement here in MATLAB exactly as I typed here. Okay? So x is the base motion. Base motion was what? Base motion? Sine of t. That's right. Yes. Look at here. Base motion was sine of t. Okay. Right. Minus x double dot. Hold on. Minus x double dot. Sine. So cosine gonna be. Can you look at the notes on what was the x that I told you in the previous class? What was the base motion? Sine of t or minus sine of t? Not here, not in the code, in the notes. Oh, okay, sine of theta. Okay. So I'm gonna say, look at here, your x of base was sine of, but I have to read all the t's. So look at all the t's are here. See, t, exactly like theta. I'm gonna say t, all the rows and the first column, exactly like that. Now but I don't need all the rows. I need one by one. I'm gonna put counter. So rows 1, column 1. The next loop, rows 2, column 1, rows 3, column 1, rows 4, column 1, rows 5. See, it's increasing. See what I'm saying now? Yes? So this is x. So x of base. Here we go. And as I told here, L sine theta plus x. So again, x of b plus L sine, but your theta, this is, right, sine theta. But I have to put here what? Counter, because I want to get frame by frame. This is your x. Now y's. Exactly, I'm typing here. 0 minus L cosine theta. 0 minus L cosine theta means multiply it. Cosine theta. Okay, done. But we are missing some part of the information. So what's that? We don't have L. So I'm coming here. I'm saying gravity is 9.81. For God's sake, everybody knows this, right? So you know that natural frequency square is G over L. So L gonna be G divided by omega n squared. Here we go. This is how we find L, length of the pendulum. Look at your notes. Right, guys? Huh? Omega n. So, but we don't need L here. So I'm gonna make it global. Global means read everywhere. This is the command in MATLAB. Global L. So I'm also putting here global L. So now when it calculates L from here, it reads everywhere. See what I'm saying? So now, see, L now is being read. See? It's not blue. Interesting, right? So now, let me put and debug the code, because you have to first run it to see that everything is right. Oh my God. I'm stupid. This size. Here we go. That's enough. So it's moving. But this is ridiculous because I have to put the axis on that. Look at here, guys. I say axis of minus 10 to 10 and minus 10 to 3. This is how you define a MATLAB. See, this is the x limit axis. This is y limit axis. Okay. So now let me stop it. Okay. Oh, it was too much. Sorry, guys. It is 2 to 2 to minus 3 to minus 3 to minus 3 to 1. See that, guys? Even that is much more. I'm sorry. Minus 1 to 1 minus 1 minus 8. Here we go. You see, guys? Base is moving based on sine of t. It's gonna back. Come on, where are you going? Oh yeah, it's gonna back. So I have to increase this. See? It's going, this is the base. And this is the pendulum that is oscillating. See? Interesting, right? Yep.
Yeah.
Okay, now I'm not done yet, man. I have too many things to do here. So here was too much. Here I have to put 0.5, and here was 0.5 as a 0.5. Then I'm gonna make it line width. I'm gonna share the code when I'm done to, and I'm gonna use it when you graduate in industry. Okay? Oh yeah, obviously. I'm here to serve you. Okay? I'm such a glorious professor. Just kidding. Okay. 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 Here we go. So what happened? Oh, okay. See, guys? Yes? So this is sine of t, the base. I have to put 1 minus 1.5. Now, let's go and add the circle. First, let me check this. Yes, hold on. Here we go. I'm going to share with you. Okay? But if you have a question, ask me now. So, first, global L, and you have to also put global L here. Okay? So, now, first I'm gonna make it grid. Okay? Make it more attractive and sexy. Now, and let me put also axis at the end. Now I want to add circle. I'm gonna say hold on. MATLAB understand your language. This is I said hold on means I have much more to plot. There is a command in MATLAB with the name of fill. Fill the area. So what area? X of the circle and Y of the circle, and with the color of the green. But we have to define X and Y of the circle, and we defined already. X of the center, X of B plus R cosine gamma, R sine gamma. Okay. So what we're gonna do, we're gonna say R of the circle, for God's sake, is 0.5. We're gonna fix later. Gamma is from, you know how to increase that, 0.1 to 2 multiplied by pi. Now we are here doing X of the circle. Is X of B, see, X of B, exactly frame by frame, plus R of C multiplied by cosine of, but gamma, okay. Gamma got to be all of that because we are covering all the radians. See what I'm saying? Now, and the Y of C is gonna be Y of B. Y of B, what is Y of B? Y of the base? 0. Right, guys? Look at here. Because it's only moving on this side, see? It never moves, so it is 0, Y of the B. 0, here, Y of B, 0. Understand, everyone? Yes? So it's gonna Y of B RC and sine gamma. Exactly what I did. You see, I started from a complex problem This is the whole picture, guys. You as a control engineer, you're gonna do that. You start from a complex problem using the basic dynamic course that you passed here, using Newton's second law and the moment equation for the mechanical systems. I'm gonna cover the old systems. You're gonna derive differential equation. If it's nonlinear, you're gonna linearize it at an equilibrium point. Okay, and based on the sign that I'm going to teach you in detail, you're going to judge about the stability of the system. Then you find the solution if you want to say that where is complex, what are the roots or poles in a complex plane. Then using the high school or middle school sine and cosine, you can make a movie of that. Then at the end, after passing this course, you can control it. Okay, there's no magic. So x of c, y of c. Okay. Now I define it here. But I am putting, because I hold on here. If I don't turn off this hold on in the next loop of the for loop, it's gonna stick all of them. So I'm gonna, let me do that. I will show you. First, let me run it. Okay. See how it does? See? We named this in the research area of the robotics control and dynamics as a stick diagram, because they are sticking together. Because I didn't turn off this hold on command. See what I'm saying? Huh? First of all, the place of that is wrong. So I did something wrong here. Hold on. X of C, Y of C. Oh, Y of base, guys, not Y of base. I'm stupid, guys. This is center. Center is x plus L sine theta. I made a mistake because I'm doing with you. I'm teaching from my mind. So this gonna be this. See what I'm saying? What was my mistake? X of center. X of center of pendulum. Right? See what I have done? Y of center of pendulum. And here is now is L minus L cosine theta. Okay, and this is x of center of pendulum and x of y of center of pendulum. See what I have done? Yes? Here, this point, this is x of circle, x of circle. X of circle is xl plus sine theta. Y of circle is minus L cosine theta. Okay, guys? Yes? Understand? So now let me no, stop. Okay. Come on. What happened? Okay. Now look at here, guys. Now this is good. Now the circle is at the end. But this is a stick diagram. See what I'm saying? So to fix it, I have to, after you plotted everything, you have to put this command, hold off, after you plotted everything. Now if I run it, this is what I get. See? Interesting, right? Yes? Okay. But you as control engineer is to fix this. You have a disturbance that is base motion, and we want to keep the angle always 45 degree here, not marginally stable. So you have to design a controller, apply a torque at the joint that make that happen. This is your function as control engineer in this class. See what I'm saying? So now for making complete, because I'm gonna send it to you and you're gonna use it in the control also. Because we have a base, this base, guys, this base. I'm gonna model it also. How? Let me go back to here. If this is the base, the x of this corner is, if it is 0, gonna be, I don't know, minus 0.5. It's y minus 0.5. This corner gonna be plus 0.5. Its y is minus again 0.5. This corner gonna be 0.05 again, but y gonna be plus 0.5. Just example. This corner gonna have the same minus 0.5 and positive 0.5. What I'm gonna do? I'm gonna start here and going counterclockwise and use the fill command. You cannot go sporadic and by random. This. No, you have to go this way or this way. Okay, clockwise or counterclockwise. Okay, so I'm gonna do that, guys. So I'm gonna say fill x of square, sorry, rectangle, and the y of rectangle, and make it green. But I have to define x of this. So x of rectangle, as I did exactly, is minus 0.5 to plus 0.5 to plus 0.5 to minus 0.5. Bingo. Look at here, guys. Minus, plus, minus is x. We can tune later. Y of that is minus 0.5, minus 0.5, plus 0.5, plus 0.5. Here we go. As we did previously. Maybe we have to tune later. See? Minus, minus, plus, plus. Let me double check the numbers. Minus, plus, minus, 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 plus, plus. Now we have x of this. See, I have two holds on. After I'm done, hold off. Okay. So let me see if it works based on this scale. Fill. Oh, I forgot this. I see. Because this is being moved by what? Being moved by base. We have disturbance. I forgot this. X of b is its x is x of base plus this. Everything is moving with the disturbance. That's right. X of b sine t. Now if I stop it. No. Okay. There we go. Looks good, yeah? Yes? Great. Now you have a marginally stable system with the disturbance at its base. Now we want to design a controller, but we have a long way to do that. I have to teach you too many things before getting there. Okay? So that's it. Even that you can add saying hold on, hold on. You say add the text saying at 0.5 and 0.5 and 0.25 and make it as 0 actually. Say this is the marginally stable page based on disturbance and font size of, I don't know, 12. Huh? Font size of 14. Okay. Yeah. There we go. Okay. I have moved it to the other way. You can add the text here. Let me fix it because I'm sharing with you. Okay. It's gonna be minus 0.2. There we go. Oh, you have to. Oh, this is minus 1. Sorry. Minus 1. There we go. Okay. Understand? So this is how we came up a logical path. That's it. I'm not sure. Because I have done this 12 years ago when I was a PhD student. Let me try this. You can say access off. There's a command that shows you. You see? Now it's like exactly like a movie that you make. Okay. Interesting, right? Okay. So now I'm gonna share it tonight to you. This code. Keep it because we're gonna work on this in several occasions together. Okay. So we developed everything. So now I want to close it. Any question? Any question? Okay. So now here we go. Let's go to our course and give you some hints, and we are done for this class. Okay, here. So guys, you saw it. Now assume that theta double dot, even this very simple linearized version, I'm giving this function as the input to the system. What is this in mathematics? What is this? Delta of t. It is impulse. Impulse to the system. Impulse is that huge kick to the table, powerful force in very short amount of time. So if I want to plot it, impulse, okay, this is time. Impulse is this. Before 0 is this, nothing. At 0, a huge amount of time, and after 0 again is 0. So now you graduated from mechanical engineering. I'm giving you this differential equation, and I give you 10 years to solve it. Who can solve this? with this input to the system, impulse. In this format, no one. No one. Why? Why you cannot solve this? Because mathematically, impulse is defined like this. Write it down. At t is not 0, how much is the value of that? How much is the value of that? Is not 0. This is t0. t0 is 0. At t0, how much is the value of this? One of you tell me. How much is the value of that? Give me a number. A huge amount of force that you're applying to the system. How much is that? Yeah, infinity simply means unknown. I don't know. Infinity. This is how we define the impulse in mathematics. So I'm giving a differential equation. The right hand side is unknown. Go and find the solution of this in time series. No way. So you have to transfer the undergraduate to linear control by linear differential equation from time. We have to go on the bridge and transfer it to frequency domain. Frequency domain. From T, we say to S domain. S. How we do it? But what I'm exposing you with the name of Laplace transform. Laplace transform. Laplace transform. This is t in second. The variable Laplace transform is defined as j or I omega. We know I is square root of -1, and the omega is the frequency, characteristic, frequency characteristic. So you have to transform this differential equation to frequency domain through Laplace transform, and we go from there eventually to domain of the frequency by next class to solve this equation. Why? Because let me tell you this, because in this course we have 4 inputs to the system. First is impulse that we are showing with delta of t. Second is step that we are showing with unit step. We are showing with this sign. It's kind of like 1. C, ramp, input to the system, that we are showing with T. D is parabolic, which is 1/2 t². We're going to apply these inputs to the system based on the block diagram I showed you eventually. Okay. On the other hand, if I cut a part of pendulum that I showed you, and this was G, the plant, and this is the output of the system, I'm going to apply impulse to the system to see how the system behaves. Then I'm going to apply step, then I'm going to apply ramp, then I'm going to apply parabolic, but in frequency domain, in S domain. Okay? Clear, guys? Yeah, T, time, ramp. Exactly, Y is equal to, X is equal to ramp, input to the system, and output is Y, right? So if I want to plot it, I'm going to go in detail the next class. As I told you, this is impulse. This is step input. Here is 0, step, because it's step. And here is 1, unit step. This is ramp, from high school. y is equal to t, ramp, and this is parabolic. Here we go. Okay, but first you have to be exposed to Laplace transform. To know different Laplace transform, then we're gonna rewrite differential equation in the form of S domain. Then we go to the first order system, second order system, stability, PID controller, root Lucas, and we go from there. Okay? See what I'm saying? Okay, so hold on first. I pause this.